Hey there, I'm going to make another video talking about some tests I've been doing with Dynamica IMU, and today I ran a test in San Francisco with one of my company's data acquisition cars to just basically make a quick sort of seemingly obvious and comparison between the Dynamica race grade IMU and a very, very expensive KVH fiber optic gyro IMU module. So what I did is I drove around this block here, which it's a little bit difficult to show in this picture, but this area down here where my mouse is and this area up here where my mouse is a fairly steep hill. It's something about 15 degrees of positive and negative pitch depending on which way you're going up or down. So I'll run this animation at 10x just to show. So here's the car, so that's ending it, and it will start again. This is the car where the arrow is here, and obviously this is 10 times the speed, so I didn't drive down the block this fast, but this shows what I did. And the thing that's so nice about driving around the block repeatedly is that it should be a consistent data set for a pitch analysis. So it should be the same pitch every loop on the two steep sections of this loop, this singular block. And so what I did is I took the raw calculated pitch output from my IMU sensor and ran just a straight up integration on we'll call it pitch rate or the angular rate of the pitch measurement axis, and wanted to compare the two to show you the effects of drift. It's pretty nice, and one of the cool things about that is that you'll see that the very expensive IMU has a very, very low drift, and it shows in the integration very, very dramatically, in my opinion. So anyway, I'll go ahead and stop this animation and roll this to the start of the test. So the first thing I wanted to show you was this is the race grade IMU integration to just show pitch. So what you'll see is that I will roll the car forward so that it's now up here at this stop sign, and I will put it on the downslope of the hill. And what you'll see here is that it's registering that the pitch is the equivalent of about 11 degrees or 11.8 degrees of pitch angle, and this is the pitch rate, what we're calling it here. So raw measurements don't tell you a whole lot, so you really need to integrate it to get something useful out of it. But what you'll see over time is throughout the test, the value will start drastically sort of drifting away from center line. So the starting point and the stopping point should be the same. So I start the test at a pitch angle of 0, which is indicated here, and I end the test at a pitch angle of 8. So the car didn't brake during this test, so it should still be 0 at the end. So that sort of perfectly highlights the drift that's present in a MIMS, sort of lower quality IMU. So I did the same thing with the output from my IMU, and it does basically the same thing, except that the internal posted measurement of pitch, which goes through a sort of black box, probably Kalman filter algorithm, outputs pitch angle reasonably accurately throughout this entire test. So the green trace here is its published pitch angle. So it is subject to some error. There's no question about it. It's difficult what we're trying to do with this thing and what that sensor outputs. Trying to calculate it without some type of GPS reference is very difficult. But it does a fairly good job in that, to begin with, it starts the test at around 0 degrees and ends the test at about the same amount. So plus or minus half a degree start to end. You will notice that some of the pitch values are exaggerated from reality. meaning that this pitch measurement here, we'll call it -7 degrees, should be the same here, which it's not, so it's -2.5, and it should be the same here, which it's still not, it's -2.5. However, it's pretty close, all in all. We could probably, there are ways that I'm thinking of currently trying to fix this to make it a little bit better, but all in all, for what it is, it's pretty good. So the green, again, is the calculated output from the sensor. It's not anything, there's no integration here. The green is the raw output from the sensor in real time. The purple is me just doing a simple integration, single integration on the rate of the pitch axis, which is Y in this case. And it suffers the same thing as the race grade does, where it starts at 0 and it just gradually starts drifting away towards the end of it. Worse than the race grade one, I should note. So kudos to them. Okay, so now we get to move on to the really expensive sensor, so this is something in the equivalent of about $10,000, I think. So this sensor is much nicer. So we'll look at this data. So this is pretty impressive. This is the calculated output. This is the live output from this GPS receiver. This is a GPS IMU, inertial survey grade IMU, or survey grade GPS system with an inertial component. So it's pretty fancy stuff. So this is the raw pitch output, is in green, and then the integration is in purple. And what's arguably more impressive than the fact that the real-time output in green is consistent. So this is 12.3 degrees, 12.6 degrees, 13.5. So could be, I tried to go the same speed throughout these, but it may not have been the case. And what's really impressive to me is that the integration has almost no drift compared to the Dynamica and the race grade one. So it's pretty impressive. But that's sort of the money that you're paying for when you buy a really expensive IMU. So I was pretty happy with that. So hope I'll continue to keep working on the IMU until I get it to a point where I feel like it's stable and reliable, and I can give them out to some people to try them out, see if it helps you guys go faster or do something more reliably. All right, thanks.